Welcome back, physics friends. Sean Nally, your physics pal here, and I'd like to speak just a little bit longer about this business of the speed of light. So in our last video, we talked about how the speed of light is the fastest speed that there is. It's the fastest of the fast. It's 299,792,458 meters per second. And what that, of course, means is that 1 meter is defined as the distance that light will travel in the inverse of that number, which is 1 over 299,792,458. That is roughly 1/300 millionth of a second. Okay, and again, this is represented by the letter C. So you remember all that, right? Well, let's talk about exactly how fast that is. So I gave you a few examples last time, 7 times more or less around the Earth's equator in a second, to the moon in about 1.2 seconds, to the sun in about 8.3 minutes. This, of course, means that you can actually use the speed of light as a de facto distance measuring tool, which is to say that the distance to the moon can be expressed as 1.2 light seconds, or the distance to the sun is about 8.3 light minutes. And for that matter, the distance to Alpha Centauri, the 3-star system, our nearest star system that's not the sun, is about 4.4 light years. Does that make sense? I sure hope so. Talked about this already. And I also showed you the animation of going from the sun to the Earth and how it seems painfully slow, even at the speed of light. But this, my friends, is a wonderful visualization tool that I'd like to show you right now. This the second link down below, this speed of light visualization tool. Let's talk about this. Take a look right here. Let's see if you actually send a pulse right over here. This is from the Inner Harbor, the aquarium actually, in Baltimore. Let's say you want to send a pulse from here to Madagascar. Maybe we've got some fish who have some friends over here in Madagascar. The distance is about 14,350 kilometers away. Look how fast that is. That is 0.047867 seconds. So that's just about 5/100ths of a second. That's actually really, really, really fast. But it can be crazier. Let's take a look at this. Here I've got the distance going from Baltimore Inner Harbor to the Washington Monument. So I can blow this up a little bit if you want to see exactly where we are here. We're right kind of in here at the Inner Harbor. In fact, again, at the aquarium. And the distance going directly there to the Washington Monument right here, that total distance is about 57 kilometers. How long does it take light to get there? Can you even tell? That's 0.000192 seconds. So, yeah, that is pretty crazy fast. 192 ten-thousandths of a second. Really, really, really fast. Okay, back to this. So again, if you have some time, play around with this. I think it's a wonderful, wonderful tool to help you visualize just how crazy fast the speed of light actually is. Okay. Now, I had defined the speed of light earlier, roughly 300 million meters per second, and that, of course, begs the question, well, what in the world is a second? So the second and the meter are defined well, they should be defined independently of each other, or at least one has to be defined before you define the other one. How about if I put it that way? So think about it this way. So the second is something kind of near and dear to your heart, you know, that basically is kind of a play on words there, because really it's about the same length as a human heartbeat. So that kind of makes sense that second would be adopted as a standard since it's so close to a heartbeat. So here is the original definition of the second. It was the amount of time required for a 1 meter long pendulum, 1 meter being previously defined as the distance from North Pole to the equator divided by 10 million. And it's the amount of time required for the 1 meter long pendulum to swing from one side to the other extreme, assuming that you have a small angle. Now, this is animated here. This should beg a whole lot of questions from you. You're probably wondering, well, how heavy does the pendulum have to be? Turns out it doesn't matter. Well, how far back do you have to pull it? It turns out it doesn't matter much, but a little. Does it matter what the string's made of? Does it matter if there's friction? Does it matter if there's air? Well, yes, it kind of does, but very, 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 very little. Enough so that nobody could tell the difference with no accurate timekeeping devices in 1795. So this definition of the second lasted for quite a while, lasted for several decades. But ultimately, it was it was replaced by a different standard. But again, the original second was the amount of time required for a pendulum to swing from one extreme to the opposite side. It would have to be a 1 meter long pendulum, and that's 1 meter from the pivot point to the center of the ball or whatever is swinging. And it's also assuming that the string is very, 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 very lightweight compared to the mass of the ball, or the pendulum bob, as it's usually called. Now, again, that standard has changed. It was changed because of the aforementioned things, like the fact that friction is not zero. It might not be a lot, but it's not zero. The fact that the string is going to have a small amount of mass. That the fact that the angle is going to make a small amount of difference. It's not huge, but it's measurable. So, the definition of the second became defined as 1/86,400th of the mean solar day, that is the average solar day. That became changed to the current definition, which is 9,192,631,770 vibrations of a particular wavelength of light emitted by a cesium-133 atom. That is, it's the time for that many vibrations to be emitted. Okay, you're thinking, well, what? So that actually comes from something we call an atomic clock. So yes, we get our second from a so-called atomic clock, which is just about the most accurate mechanical timekeeping device that exists. It uses decays from a cesium-133 atom. Now, as it turns out, we could also use pulsars. They work beautifully, but not everybody has easy access to the tools required to measure a pulsar, whereas any country with a Bureau of Standards and Measurements would have access to an atomic clock. So that's our current standard of time. Now enter the kilogram, the standard of mass. This is a peculiar one, peculiar standard actually. The kilogram was originally defined in terms of water. If you take a cubic decimeter, now that is 10 centimeters by 10 centimeters by 10 centimeters, that amount of volume is defined as something we call a liter. You've all seen a liter before. You probably have a liter bottle of water, or you've certainly seen 2-liter bottles of soda before. The 1 liter container is it's 1 cubic decimeter, and that is again 10 centimeters by 10 centimeters by 10 centimeters. So 1 liter or 1,000 milliliters. Now, if you fill it with water, that was the original definition of the kilogram. And in fact, it has not changed much. But as it turns out, and you might know this if you've studied a little bit of chemistry, water's got some weird properties, and there are many experimental issues with this. For example, you can overfill a container of water, and the water will rise above, kind of hump above it. And that makes it difficult to know when you have it completely full or overfilled. That's one of the issues. Surface tension allows you to do that. There's also the meniscus issue for water adhering to the sides of the container. There's also the fact that you have to have water at standard temperatures and pressures. Turns out that, as convenient as this may seem, it's actually not ultimately accurate enough, or maybe precise enough is a better way to put it, when we are measuring things like itty-bitty particles that are on the order of a billionth of a billionth of a billionth of a thousandth of a kilogram. So it got changed decades later to, believe it or not, a chunk of metal kept in Paris. The double bell jar that you see in front of you had a cylinder of platinum iridium, which is kind of crazy to think about the standard being defined by a chunk of metal, but it was for decades. Now that finally changed in 2018 after many years of different experiments, competing experiments to change the standard. It was changed formally in 2019, but approved in 2018. The new kilogram was determined by an electromagnetic tool called a Kibble balance. And what happens with the Kibble balance is it uses essentially an electromagnet that balances a weight. Looks kind of like this, actually a lot like this. That's the picture of it on the left, and there's a schematic picture on the right. And essentially you've got an electromagnet here. You run a certain amount of measurable current through it, and it will electromagnetically attract the weight. And based on the amount of current going through it, you can infer what 1 kilogram is, or at least you can define 1 kilogram. And that's what we use now. The biggest improvement over this is, of course, that the kilogram is no longer based on the arbitrary chunk of metal, even though that had historical basis. It's based on a measurable, repeatable thing that anybody in any good lab could effectively come up with. I should also point out here that, believe it or not, platinum iridium, despite the fact that it doesn't really rust, actually slightly evaporates over the course of decades. It's lost a few micrograms, which is nuts to think about. So there you have it. So, are there other SI standards? Whoa, yes there are. There are a few. Volume is, of course, measured in liters, and that is 10 by 10 by 10 centimeters, or 1.0000028 decimeters cubed. That's the actual official definition. A milliliter is approximately equal to a cubic centimeter. They are well within a fraction of a percent, even though they're not precisely the same thing. Temperature is generally measured in Celsius in SI. Occasionally there's need to measure temperature in terms of the absolute temperature scale, which is a scale that starts at 0, or absolute 0, the temperature which there is no molecular motion. Now the offset from degrees Celsius to Kelvin is 273.15. So Kelvin is actually what you get when you start with no motion. In degrees Celsius, when you add 273.15 to degrees Celsius, that will give you the temperature in Kelvin. Or another way to think of this is that negative 273.15 degrees Celsius is equal to 0 Kelvin. And there's some other ones too. There's the ampere, there's the candle, there's the mole, which you may have heard of if you've had chemistry before. There are plenty of them. There's actually quite a few goofy units too that are a whole lot of fun to read about. I'll probably talk about those a little bit later. Yeah, they're kind of cool, actually. Also, there are metric prefixes, or prefaces if you prefer. These are the biggies right here. Well, I think this is all of them. I'm not 100% sure about that, but these are the ones that you are likely to see pretty much ever. I want to point out the ones that are probably the most important. The ones that are most important are centi, milli, micro, nano, kilo, mega, giga, and tera. Now let me go back. Centi is 100th, or 10 to the minus 2. Milli is 1,000th, or 10 to the minus 3. Micro, 10 to the minus 6. Nano is 10 to the minus 9. Micro, that is it's a millionth, and a nano is a billionth. Pico is a trillionth. If we go in the opposite direction, there's others that you have probably seen, like for example, the kilo is 1,000, mega is a million, a billion is giga, and trillion is tera. If you know anything about computers, you've heard of terabytes, gigabytes, megabytes, certainly kilobytes. And these are quantities of bits of information. And you can say a whole lot more about that, because that is how we actually manipulate data in computers. If you're interested in a little bit more, here's a whole lot of links for some background about the SI scheme of units. So in our next class, we're going to be talking about unit conversion, and this is great because this allows you to switch between units. Let's say, for example, you want to switch from kilograms to pounds, or if you want to switch from seconds to days, seconds to years, if you want to switch from inches to light years, anything like that. It's not too hard to do. There's a skill that is really important. There's a way we do it. It's called factor conversion, or factor labeling, or just unit conversion, and I'll teach you how to do that in our next time together. But just to give you kind of a way to think about this, how would we do a problem like this? If you had 27 quarters, how many dollars is that? That's something you can think about. Now, that's one you could probably do in your head, but knowing how to do that problem in a methodical way allows you to see exactly how we do all conversions, especially when they get more complicated. Like, how do you convert something like a mile per hour to a meter per second, or vice versa? How do you convert a meter per second to a mile per hour? I've said that, for example, that the speed of light is roughly 300 million meters per second. How many miles per hour is that? How do we do that? Sure, you can look it up on Google, but ultimately you want to be able to actually do that yourself, because it allows you to solve for some way more interesting problems. Like, for example, let's say you're painting a house. How many gallons of paint would you need? So that's a unit conversion skill. Okay, see you soon. See you on the moon.